So we got this game. The machine makes them 29.5 millimeters wide, but of course nothing's perfect. So they take a random sample of 50 cubes and they measure their width. And then we have this fathom output over there where it says title collection one. Um, and you can figure out what each output is. We haven't really looked at Fathom software at all because we don't own it. So if we owned it, we would play with it, but we don't. And I really prefer owning the TI stuff, but obviously those go together, right? And you can see that the order is correct. It makes sense. You don't need to know how to read a Fathom output to figure out, right? If you want the block to be 29.5 millimeters, that looks like a fair mean, right? And then the count is 50, so you see that it's actually going in this order. Let's interpret the standard deviation and the standard error. So A, what, on average? Blocks will be blocks will be our standard deviation 0.09 millimeters from the mean. Just again reinforcing what standard deviation is. And then the second part, standard error. So the standard error is right there. So what does standard error tell us? It tells us that if they were to repeatedly take samples of size 50, we would find that on average, they vary by, or the widths vary by 0.013, right? I didn't say random sample of size 50. Vary by 0.013 on average. I'm not very good English. Just trying to take it back a little bit to chapter 8, talking about confidence intervals. And the first part is taking it back, way back. Look at chapter 1. We interpreted standard deviation. Right. Do these data give convincing evidence that the mean width of cubes produced this hour is different from 29.5 millimeters? Well, I mentioned that we were taking it back to chapter 8, right? Which was talking about confidence intervals. We have all the information we need to get a confidence interval, right? We have an X bar value, and we have our standard error. Let's see. We're going to have to see, do we want to do this at what confidence level? I want to look at a confidence interval anyways. So let's look at a 95% confidence interval, and this is going to tie into the actually next question. So our P star value is what we need, right? So I'm going to need a. All right, so we have 49 degrees of freedom. All right. So for 95 degrees of freedom, we'll use, or sorry, for our 95% confidence interval, forget degrees of freedom, we're going to use 1.96 as our critical value. And when we multiply that times our standard error, oops, 0.013. All right, so we can create a confidence interval by making a quick calculation. Why am I? Go ahead and calculate that interval. Point 2548. All right. Well, our mean that we are looking for is in there, right? Because it was 29.5, right? Yeah. So just barely, but it's in there. I would say that probably they're not different. So there's one approach. We could look at a confidence interval and see at the 5% level, and we're actually going to relate this to, I want to do this all at once so that we can relate this to looking at testing a hypothesis at the alpha level of 0.5 in comparison to looking at a confidence interval at the confidence level of 95%, right? You can kind of see how those two things might be related because of 5%. So we created a confidence interval. I don't know why that just happened. Let's go ahead and perform inference. I'll just write that this is at the 95% level. So P, our parameter of interest, is the mean width of cubes produced by this machine. We're going to try to go a little faster. Our hypothesis, well, do we care if they're bigger or smaller, or just not equal to that? It's different from, right? So this is what we're gonna, when we're testing our hypothesis, we're looking for that, right? Greater than, less than, or different from. So our hypothesis is going to be that mu is 29.5. And our alternative hypothesis is that mu is not 29.5. Right. We have to check our assumptions. Hey, good news. It is greater than 30. So that should be good enough. Also, the data comes from an SRS. I got excited because we finally had a sample that was greater than 30, so we could skip all the looking at the data and entering it in, right? We could just say, hey, the data comes from an SRS. The sample size is greater than 30. And is it the case that do we think that 50 times 10 is going to be less than or equal to the entire amount of cubes produced? Yeah, for sure. I'm sure they make a lot more than 500. Yeah, cool. And we're gonna do a t-test. And it might be nice to say the conditions are met. To perform a t-test. One sample t-test, you could also say, but it's assumed that if you don't say it's a two sample t-test, you're only using one sample. All right. This one's going to go a lot faster because we don't have to look at all the data, enter it into the calculator and all that. We get our test statistic, which is going to be z equal to our x bar, which is going to be 29.4846 minus 29.5. We need our standard deviation. What was that? 0.09 divided by 0.09 divided by the square root of 50. Probably going to be an approximation. I'm going to get out my handy dandy calculator. Oops, where are you? There you are. Ooh. Okay, because I don't need to put a bunch of lists and stuff in, I can do this just using my scratch pad. So I can just hit the calculator button, and I can hit menu, statistics, stat tests, we'll go ahead and choose a t-test. And now we are not going to use data, right? Now we're going to use statistics. Hit OK. And this will be 29.5. X bar from our sample was something 29.4846. Our standard deviation was 0.09. and it's 50. And our alternative hypothesis is fantastic, right? That they're different. I can hit enter, and I get my t statistic. I get a p-value. Did I write z? Oh, silly me. Sorry. Silly. T. And T is negative 0.209 and negative 1.21. Let's go with that. Okay. So we got our test statistic. Oh, let's obtain a p-value. So we're looking at the probability that T is between, my bad, that T is between, no, we want the opposite. Let's look at that T is less than 1.21. But aren't we really actually looking at 2 times that? Why are we looking at 2 times that? Because what does our picture look like? We got 2 tails. Because we are a savage beast. So it looks a little something like that. So then I can just find the area to the left of negative 1.21 of my t-distribution and then multiply it times 2, right? Okay. That's fantastic. It turns out that we have a value for that already from our calculator, which is 0.232. We should put our degrees of freedom as well. And then we have done it. Oh, let's make a decision. So if we haven't been told the alpha level, we will assume an alpha level of 0.05. So in order to make a decision, we will reject correct. We will reject. I don't want to say it in all cases. I just want to say writing. Alpha equals 0.05. Okay. We'll state our answer in context. There is not convincing evidence you mean with chips, you mean with ice blocks, cubes, you mean with cubes. Is different. Boom. Did a confidence interval, did some inference. That's pretty thorough right there. Alright. And it makes sense, right? So it makes sense that if we were to look at a 95% confidence interval, we should get the same result as we would get testing our hypothesis at the alpha equals 0.05 level. It's almost, the two things are very, very, very closely related. Fantastic, and I believe I jumped the gun. And that's what our next one is looking at. So we got the fathom output for the true mean width. And they wanted us to interpret a confidence interval, which we actually created. And we actually did this in the last example. I think I studied my notes on Friday and just jumbled them all together. So that's all right. We did it. So we didn't interpret the confidence level. Oh, the confidence level. We did not do that. So, the answer is yes for all of them, right? We did A already. Let's talk about B, because we can't forget how to interpret a confidence level, right? So the idea for B is for repeated samples of size 50, yeah, 95% of our confidence intervals that we would create would contain that true mean. Yeah? Okay, cool. Right. About 95% is the only difference that they're saying. So, for repeated samples, of size 50, we expect of 95%. Of 95% confidence intervals. I'm wording it in a really weird way. Theirs was much more verbose and said the same thing. But mine had this weird 95% of 95%. It's okay. It says the same stuff, right? Confidence. And I can spell. Confidence. Yay for us. Look at us go. We're getting so many problems done today. All right. Ooh.